We have started to deal with the problem of collision of two particles or two bodies uh, when the collision is elastic in the previous lecture. And in this regard, you have seen in the previous video the problem of collision, elastic collision of two bodies, particularly in laboratory frame of reference. Now today we will deal with the same problem, but our frame of reference will be not lab frame but center of mass frame. It means the aim of this lecture is to discuss the problem of two-dimensional elastic collision between two bodies in center of mass frame. Actually, in this problem, our aim is to find the final velocities of the colliding bodies after collision. And we will also learn about how we can relate the angle of scattering and the angle of recoil in the laboratory frame of reference to the angle of scattering and angle of recoil in center of mass frame. So these are the two key problems which will be dealt. Okay. So let us see. I have shown in this figure, you can say this is figure 1. There are two particles or two objects of masses m1 and m2. This is a particle of mass m1 and it is moving with velocity u1, as you can see in this figure. And the another particle of mass m2 is stationary, it is at rest. So I have marked here that its velocity u2 is 0. Okay. And this particle of mass m1 moving with velocity u1 collides with the mass m2 which is at rest. Actually these velocities marked here u1 and u2 that has been actually measured by an observer fixed in the laboratory frame. We are not talking here about the center of mass frame, but you can say that u1 is the velocity of mass m1 before collision in lab frame, and u2, which is 0, this is velocity of mass m2 also observed by the observer fixed in the laboratory frame. Okay. But when the same phenomenon will be observed by an observer who is fixed in center of mass frame, then the velocities of the objects will appear different. So in this second figure I have shown that when this collision is observed by an observer fixed in center of mass frame, then before collision u1 dashed, this is velocity of mass m1, okay, that is velocity of projectile you can say, and u2 dashed is the velocity of mass m2 before collision in center of mass frame. Okay. Then what will be these u1 dashed and u2 dashed in terms of u1 and u2? You can easily find by the velocity transformation equation. You have learnt about the center of mass frame. It is a frame attached to the center of mass of the system. Okay. And so this frame will move with a velocity equal to the velocity of center of mass with respect to the lab frame. So now let us see what will be actually the velocity of center of mass of this colliding system. As you have learnt in previous lectures that velocity of center of mass of these two particle system will be what? That will be this velocity v is actually the velocity of center of mass with respect to lab frame. Mark it. V is the velocity of Cm with respect to which frame? Laboratory frame. And that will be equal to m1 u1 plus m2 u2 divided by m1 plus m2. Okay. This formula you have already learned earlier. But as you can see in laboratory frame, our mass m2 is stationary, its velocity u2 is 0. So the velocity of center of mass, this capital V, with respect to the lab frame, that will be equal to what? That will be simply m1 over m1 plus m2 times u1 because u2 is 0. Okay, and you can see this equation that the bracketed term is a dimensionless number because it is ratio of two masses, and this is a positive number because mass is always positive. So you can say that this velocity v, which is velocity of center of mass with respect to lab frame, is equal to a number, positive number, multiplied by the velocity of particle of mass m1, which is u1. So you can say that this velocity v, that is velocity of center of mass, and the velocity of particle of mass m1, that is u1, both are in same direction. So you can say that if u1 is directed along x-axis as we have assumed, then according to the laboratory frame observer, the center of mass is also moving with a velocity v in x direction. This velocity is with respect to the lab frame. Okay. Now, what will be the velocity of the particles m1 and m2 before collision in center of mass frame? That can be easily obtained by the velocity transformation equation, or you can say that by the concept of relative velocity or by the Galilean transformation. This you have learnt in the lower classes, that is in the chapter of kinematics, which is called relative velocity. So here you can see with respect to the lab frame, velocity of particle of mass m1 is what? This is u1, okay, before collision. And there is a frame which is moving with respect to velocity v, which is called center of mass frame. Then with respect to this frame, that is with respect to center of mass frame, velocity of this particle m1 will be what? If it is u1 prime, then according to velocity transformation equation, this will be u1 minus v. V is the velocity of frame, which is called center of mass frame. Okay, and similarly, the velocity of the particle of mass m2 before collision in center of mass frame. If you assume that this velocity is u2 prime, then that will be equal to u2 minus v. But since u2 is 0, we have assumed, so this u2 prime will be simply equal to minus v. So u2 prime is just in opposite direction of the velocity of center of mass. Okay. In fact, we will find later on this u1 dash and u2 dash substituting the value of this capital V, which we have obtained here. But before that, you can see that when this phenomenon is observed in laboratory frame, then before collision, you have seen that mass m1 is moving with velocity u1 and mass m2 is stationary, so its velocity is u2 is 0 in laboratory frame. And you have learnt in the previous lecture that when this mass m1 gets collided with mass m2, then after collision, the projectile of mass m1 moves with velocity v1, making an angle theta 1 with the initial direction of motion of m1, that is with x-axis. u1 is actually directed in x direction. Okay, and the target, whose mass is m2, now recoils at an angle theta 2 with the initial direction of motion of m1. Okay, and its velocity is v2 after collision. All these things you have learnt in the previous lecture. So this figure, second figure, you can say represents the status of motion of the two particles after collision in laboratory frame. Okay, and as you have assumed that after collision, v1 is the velocity of mass m1 and v2 is the velocity of mass m2 after collision in laboratory frame, not in CM frame but laboratory frame. Okay, now we assume that this v1 dash, this is velocity of mass m1 after collision in center of mass frame, and v2 prime is the velocity of mass m2 after collision in center of mass frame. We assume. Then again, from the velocity transformation equation, or you can say by the concept of relative velocity, or you can say by the Galilean velocity transformation equation, what will be this v1 dash? Since v1 is the velocity of mass m1 after collision with respect to lab frame, and v1 dash is the velocity of same particle with the moving center of mass frame. So with respect to the moving frame, that is center of mass frame, its velocity v1 prime will be equal to what? That will be v1 minus v, where v is velocity of center of mass, or you can say v is the velocity of moving frame. And similarly, v2 prime will be equal to v2 minus v. Okay. Finally, we will find this v1 prime and v2 prime by substituting the values of v, but here I have not calculated it. Just after some time we will calculate it. But before that, now see this phenomenon in the center of mass frame. As you know that our center of mass of the system is moving with a velocity v with respect to lab frame. With respect to lab frame, its velocity is v. But if you consider this center of mass as a frame, it means you are considering a frame attached with this center of mass. Then you know in the center of mass frame, the center of mass itself will be stationary, because then you have to find the velocity of Cm with respect to Cm. The velocity of center of mass with respect to center of mass, that will be simply v minus v, that will be 0. And so in a laboratory frame, the center of mass of the particle is at rest. With respect to lab frame, center of mass frame is moving with velocity v, capital V. But in Cm frame, this center of mass is at rest. And in the previous lecture you have learnt, in the first lecture on this collision, you have learnt that if your aim is to find the total momentum of the system in any reference frame, then you have you can find it by a simple concept. Multiply the total mass of the system by the velocity of center of mass in that frame. That will give you the total momentum of the system in that particular frame. So if your aim is to find the total momentum of these two colliding particles in center of mass frame before collision and after collision, what will be that? You know, before collision in Cm frame, velocity of mass m1 is u1 dashed. So m1 u1 dash, this will be the momentum of mass m1 in Cm frame before collision. Okay. Similarly, m2 u2 prime, this will be the momentum of mass m2 before collision in center of mass frame. So this sum of m1 u1 dash and m2 u2 dash, this is the total momentum of our system with respect to center of mass frame before collision. Okay. But as you know, the total mass of the system is found simply by multiplying the total mass of the system by velocity of center of mass. Okay. So we can write it, this will be m1 plus m2 into velocity of center of mass with respect to center of mass. But velocity of center of mass with respect to center of mass, if you say it is v dash, that is 0. So v dash will be 0 and hence this result will be 0. So you can say that the total linear momentum of this colliding system before collision in center of mass frame is equal to 0. Okay. So m1 u1 dashed plus m2 u2 dashed, this is equal to 0. Okay. And so you can say that m1 u1 dashed is equal to minus m2 u2 dashed. Okay, this minus sign actually implies that u1 dashed is just in opposite direction of the u2 dashed. So I have shown here in this figure, you can see that if u1 dashed is directed in positive x direction, u2 dashed is directed in negative direction. Okay, so in center of mass frame, both of these particles are moving towards each other. In lab frame, m2 was at rest and m1 was approaching m2. But in CM frame, the observer finds that the both particles are moving towards each other with velocity u1 prime and u2 prime. Okay, so these are in opposite direction. Similarly, you can also say that after collision in center of mass frame, what is the total momentum of the colliding system? This will be m1 times v1 prime plus m2 times v2 prime, because v1 prime and v2 prime, these are velocities of m1 and m2 after collision in center of mass frame, and that will be again equal to total mass of the system multiplied by velocity of the center of mass in center of mass frame, but that is 0, so this result will be also 0. And you can say that m1 v1 prime is equal to minus m2 v2 prime, and this minus sign again implies that v1 prime is just in opposite direction or anti-parallel to v2 prime. So you can see in this figure, I have marked here that if v1 prime is directed, let us say in this OA direction, then v2 prime is directed in OB direction, and both directions are just opposite. Okay. Actually, in this case, you will see that the magnitude of the velocity in center of mass frame before and after collision does not change, but its direction change. We have assumed that with the direction of the velocity of center of mass, velocity of center of mass is v with respect to the lab frame, and this is directed along x-axis, and I have assumed that this particle of mass m1 is moving, making an angle theta with this direction v, and similarly this m2 will also move at same angle theta but with the negative x direction. Okay. Now as we have considered, our collision is elastic, and you know in case of perfect elastic collision, the total kinetic energy of the colliding system before collision is equal to total kinetic energy of the colliding system after collision. In some books it is written that kinetic energy remains conserved, but this is not correct. This is not a correct statement. You should say that total kinetic energy before collision and total kinetic energy after collision will be equal. It does not mean that kinetic energy remains conserved. Okay. But I am talking about the motion in center of mass frame, and you have seen that in center of mass frame, velocities of m1, m2 before collision was u1 prime and u2 prime. So the total kinetic energy of this colliding system before collision in CM frame, this will be half m1 u1 square, u1 dashed square plus half m2 u2 prime square. And after collision, this will be half m1 v1 prime square plus half m2 v2 prime square. Okay. Now, as you have seen that velocity of the first particle of mass m1 with respect to the center of mass frame before collision is equal to u1 minus v. But as you have learnt that this v, which is velocity of center of mass with respect to the lab frame, this is equal to this much, which I have defined in equation 1. So let us substitute now the value of v here. So when we will put the value of v, our result will be u1 times 1 minus m1 over m1 plus m2. And after simplification, this result will be u1 prime equal to this much. This is m2 divided by m1 plus m2 times u1. Okay. So you can see that this u1 prime is in the direction of u1. It means velocity of m1 before collision in CM frame and also in lab frame are in same direction. Okay. Now let us find u2 prime. You have seen that u2 prime is equal to what? This is minus v. We have already seen here. This u2 prime is equal to minus v. Okay. So u2 prime is equal to minus v, and v you have seen that is equal to m1 divided by m1 plus m2 into u1. So u2 prime is equal to minus this much. So you can see that this u2 prime is just anti-parallel to u1. Actually that I have shown in this figure. You can see it here that u1 prime is already in the direction of u1. You can see this is u1 and u1 prime are in same direction. u2 is 0, but u2 prime, which is velocity of m2 in CM frame, that is in just opposite direction of u1 or u1 prime. Okay. This I have shown in that figure. Okay. So I have written that this u2 prime is anti-parallel to u1. Okay. So u1 prime is parallel to u1 and u2 prime is anti-parallel to u1. u2 prime is anti-parallel to u1. It's right here u1, not u1 prime. This is u1. Okay. Now, if you will take the magnitude of these two velocities, see, when we will take modulus of equation 3, then this will be simply u1 prime equal to m2 divided by m1 plus m2 into u1, and we will also take the magnitude of this velocity u2 prime here, but I have written here the minus sign to show that this u2 prime is in opposite direction of u1. Okay. So modulus of u2 prime, this is minus m1 over m1 plus m2 times u1. Okay. Now you know the magnitude of u1 prime here, the magnitude of u2 prime here. So let us find the ratio of these two velocities. So u1 prime over u2 prime, you can see the values of u1 prime and u2 prime, that will be simply equal to minus m2 by m1. And so you can say that u1 prime is equal to minus m2 by m1 into u2 prime. Okay. This is the relation between the velocities of the two particles before collision in center of mass frame. Okay. If you can see m1 will be equal to m2, then u1 prime and u2 prime will be equal in magnitude but opposite in direction. Actually, in the similar manner, as you have derived this relation that u1 prime is equal to minus m2 by m1 into u2 prime, in the similar manner you can also find that this v1 prime will be equal to minus m2 by m1 into v2 prime. I have not derived it, but in the same manner you can find it. Here I have obtained u1 prime and u2 prime. So in the similar manner you can find the v1 prime and v2 prime. Okay. So v1 prime will be equal to minus here not write this vector sign. Okay. This is magnitude. So v1 prime is equal to minus m2 by m1 into v2 prime. Now we will substitute these values of u1 prime, okay, u1 prime and v1 prime in this equation, which I have written for the kinetic energy of the colliding system. So at the place of u1 prime and v1 prime, we will put the value which we have just obtained. So after substituting the value of u1 prime and v1 prime, what will be your result? You can see this will be half m1, and there is u1 prime square. U1 prime square will be a square of this much, so this is m2 by m1 whole square into u2 prime square. The second term is at each. Okay. Now in RHS, the first term was half m1 v1 prime square, but v1 prime is this much, so square it. So this will be half m1 m2 by m1 whole square v2 prime square. After squaring, this minus will become plus, and the next term is half m2 v2 square. Okay. Now you can see in LHS you can take u2 prime square over 2 as a common factor. Okay. Then in first term there will be m2 square by m1, and in second term m2 remains. Okay. Similarly, in RHS we can take v2 prime square by 2 as a common factor, and the remaining terms will be m2 square by m1 plus m2. Now you can see this bracketed term will cancel out, this 2 and this 2 will also cancel out. So you can say that u2 prime square is equal to v2 prime square, or you can say that u2 prime is equal to v2 prime. This fact I have told you earlier, that in center of mass frame, the velocity of the particle of mass m2, you can say, in magnitude are same both in before collision and after collision. Before collision, velocity of mass m2 is u2 prime, and after collision its velocity is v2 prime in center of mass frame, and you can see both are equal. So the magnitude of the velocity of the particle of mass m2 does not change after collision in center of mass frame. Similarly, instead of calculating the value of u1 prime and v1 prime, if you will calculate the value of u2 prime and v2 prime and then substitute in the same equation 2, then you will get the similar result, and that will be u1 prime equal to v1 prime. So this result actually shows that after collision in center of mass frame, the velocity of the colliding particles does not change in magnitude. It means before collision, the velocity of mass m1 in CM frame was u1 prime, and after collision it is v1 prime, but both are same. Similarly, the velocity before collision of mass m2 was u2 prime, and after collision it is v2 prime, and you can see both are equal. So only the direction of the velocity will change after elastic collision in center of mass frame. Magnitude will not change. So in this figure I have shown that this you will see that this direction is not along x-axis, but I have assumed that v1 prime and v2 prime are making an angle theta with the x direction after collision. So there is only a change in direction, not in magnitude. Okay. Now our aim is actually to find what will be the value of the velocity of the two particles after collision in center of mass frame. And you have already obtained it. You know, in CM frame, velocity of particle of mass m1 after collision in center of mass frame is v1 prime. But you can see that v1 prime is equal to u1 prime. Okay. This will be just okay, don't worry. Okay. So you can see v1 prime is equal to u1 prime. And what is this u1 prime? We have already calculated here. See here. u1 prime we have already calculated. So the magnitude of the velocity of the first particle of mass m1 after collision in CM frame, this is v1 prime, which is equal to u1 prime, and that is equal to this much. This is m2 over m1 plus m2 into u1. Okay. Now again we can see that v2 prime, which is the velocity of the second particle of mass m2 after collision in CM frame, that is equal to its velocity in CM frame before collision, that is u2 prime. And u2 prime we have obtained here, you can see. So you can say that this v2 prime will be equal to u2 prime, and that is minus m1 over m1 plus m2 into u1. Okay. So this first part of today's problem has been solved. As I have told you earlier that our aim is to find the velocity of the colliding bodies after collision in center of mass frame. And in these two equations A and B, we have obtained what will be the velocity of mass m1 and m2 after collision in center of mass frame. So v1 prime and v2 prime we have obtained. Now we will see the second part of the problem. In second part of the problem, what we will actually learn. You can see this angle theta, you can say this upper angle theta, this is the angle of scattering of mass m1 in center of mass frame. Okay. And in this figure, you can see this angle theta 1, this is angle of scattering of mass m1 in lab frame. Now our problem is how to relate this theta 1 with theta, or this theta 1, that is angle of scattering in CM frame, theta 1, that is angle of scattering in lab frame, and theta, which is angle of scattering in CM frame, how these two angles are related. Okay. Again, we will also find that how this angle of recoil, that is theta 2, this is angle of recoil in lab frame, and this angle theta, which has been marked in lower side, this is also angle of recoil but in center of mass frame. How these two angles are related? This is our prime problem now. Okay. And let us see how we can easily solve this problem. Actually, solving this problem, you have to see those figures. You have seen that in the lab frame, velocity of the particle of mass m1 after collision was v1, making an angle theta 1 with the x direction. Or you can say in this direction there is velocity of center of mass. Okay, you have seen. Now, velocity of a particle in a stationary inertial frame and velocity of a part of the same particle in moving inertial frame, how they are related. You know, the velocity of particle of mass m1, which is v1, whose value in this y direction will be v1 sine theta 1. Okay. And if you want to find the velocity of the same particle in the center of mass frame and how they are related, from the concept of relative velocity, you can say that velocity of m1 in y direction, which is v1 sine theta 1 in a lab frame, that will be equal to velocity of the same particle in y direction in center of mass frame. In center of mass frame, this is v1 dashed making an angle theta with x-axis, and its x component will be v1 dashed sine theta. Okay. And center of mass is already moving in this direction with velocity v with respect to lab frame. So this v1 sine theta will be equal to v1 prime sine theta plus v cos 90. It means you have to consider the component of this v in y direction. But since v makes an angle 90 degree with y direction, so this will be v cos 90, which is 0. So you can say that v1 sine theta 1 is equal to v1 prime sine theta. Okay. Similarly, for for x direction, velocity in x direction in lab frame, that is v1 cos theta 1, and that will be equal to velocity of the same particle in center of mass frame in x direction plus velocity of center of mass in x direction. So that will be v1 cos theta 1 will be equal to v1 prime cos theta plus v cos 0, because center of mass is already moving in x direction. Okay, so this will be v1 prime cos theta plus v. Now, to relate theta 1 with theta, simply divide this equation 9 by the equation 10. So you can see in LHS v1 will cancel out, and sin theta 1 by cos theta 1, that will be equal to tan theta 1. And in RHS there will be v1 prime sin theta divided by v1 prime cos theta plus v. Now let us take v1 prime as a common factor in denominator. Then you can see that this v1 prime will cancel out, and your result is tan theta 1 equal to sin theta divided by cos theta plus v by v1 prime. But what will be this v by v1 prime? You can easily see. You have learnt that this v is equal to this much. This is m1 over m1 plus m2 into u1, and v1 prime you have seen earlier, this is this much. Already these two equations you have learnt earlier. And so v over v1 prime is this much, m1 by m2. So let us substitute m1 by m2 at the place of v by v1 prime, and you will get tan theta 1 equal to sin theta over cos theta plus m1 over m2. This is the relation between theta 1 and theta. That is the angle of scattering in lab frame and angle of scattering in center of mass frame. This is the relation. Now we will relate the angle of recoil in center of angle of recoil in lab frame and angle of recoil in center of mass frame. And for that again you have to see those two figures. See here. See this figure and this figure. In x direction, the velocity of m2 after collision will be v2 cos theta 2. Okay, v2 cos theta 2 in x direction, and its component in x direction will be minus v2 cos theta. Minus v2 cos. Why minus? Because this is in negative x direction, and Cm is moving with velocity v in with respect to lab frame in x direction. Okay, so by the same Galilean transformation, you can say that v2 sin theta 2, when you will take the y component, then v2 sin theta 2, this will be equal to v2 prime sin theta plus v cos 90, that will be equal to v2 sin theta, and v2 cos theta 2, that will be equal to v minus v2 dash cos theta, because v and v2 dash cos theta are in opposite direction, you have seen. Now again we will divide this equation 11 by equation 12. v2 will cancel out, and this will be tan theta 2, and in RHS you will get v2 prime sin theta by v minus v2 prime cos theta. Again we take this v2 prime as a common factor in denominator, and then this will cancel out, and your result is tan theta 2 equal to sin theta over v by v2 prime minus cos theta. But what is this v by v2 prime? You can see, you have learnt earlier that v2 prime is equal to u2 prime, and in vector form you have seen that u2 prime is equal to minus v. It means in magnitude u2 prime is equal to v, but in direction it is opposite. So you can say that modulus of minus v by modulus of u2 prime, which will be written as v by u2, that will be equal to V by V2 prime, because V by U2 prime, not U2. Okay, U2 prime. And you can see that this U2 prime is equal to V2 prime. So this is V by V2 prime, and that is equal to 1, because both are equal. So at the place of this V by V2 prime, we will write 1, and hence tan theta 2 will be what? That will be equal to sin theta divided by 1 minus cos theta. And this is the relation between theta 2 and theta. Here theta 2 is the angle of recoil in lab frame, and theta is the angle of recoil in center of mass frame. So in this way we have completed both parts of the problem. First of all, we have obtained the final velocity of the particles after collision in CM frame, and then we have seen how the angle of scattering and angle of recoil in lab frame and in center of mass frame are related. I hope you have clearly understand this calculation. So go through the video, watch the complete video, write down in your notebook. Everything will be clear to you. Thank you very much.